Hello guys, welcome to our geometric modeling presentation on a topic Advanced Surface Construction Techniques by Team Victoria, and present to my teammates, myself Subhash, and the topics I'm going to discuss are swung surfaces and skin surfaces, and the rest of the skinning surfaces topics will be covered by Nikhila, and she continues with explaining about the skin surfaces revisited, and Vijay Sriharsha is going to continue with the swept surfaces and a part of the Gordon, and Srikar Rao will be completing the Gordon and the rest of the cone surfaces with some few design examples. So getting into technical details, advanced surface construction techniques means we are going to discuss about different types of topics in advanced surface construction techniques, which are like swung, skin, swept, Gordon, and cone surfaces. So these surfaces are helped us in designing an object or a 3D model and trying to bring it to life. So here we are going to consider a group of curves which try to interpolate creating a NURBS, which means non-uniform rational biases spline surface. So getting into swung surface. A swung surface extension to the surface of revolution. So usually a swung surface has two kinds of curve. One is a profile curve and one is a trajectory curve. So profile curve gives the outline structure of the object. So a single line structure, and when it is done on a 3D plane, it is rotated around the axis in a circular form. But what the work of the trajectory curve is to make sure that the object does not get rotated in a 360-degree angle in a circular form, but the desired shape we want it to. So the trajectory curve rotates the image and gives us the expected image. So here, where a profile curve rotates about the axis of revolution and its degree of rotation is controlled by the trajectory curve. So the points are starting from P1, P0, P1 to P5 is the profile curve, and the point starting from T0, T1 to T10 is the trajectory curve. So all the points on P0 to P5 is a profile curve on XY and XZ plane, and here the formula is PU equal to 1 to summation of n Ri PU of Pi, and all the points are starting from T1 to T10 on our XY plane, and for that P of V summation of j equal to 0 to n RJQ VTJ. And the swung surface can be defined as SU comma V is alpha into PZ into UTX into V comma alpha into PX UY into TY V comma PZ of U, where alpha is an arbitrary common notation. So moving on, the swung surface S of U of U comma V is a curve obtained by swimming at the profile curve P of U over the trajectory curve T of V, results in the equation S U comma V 102 notation N and J 02 summation of M R I P Q J Q U V Q I J, where Q I J is alpha, the formula which I mentioned before, and alpha is arbitrary constant. Next example of swung surface is the design which I'm using here, and when we are adding all the control points and taking the arbitrary constant double alpha has 0.12, then and applying weights, then the all the profile and trajectory curve summation gives rise to this kind of object as an output, where P being the profile curve and the T being the trajectory curve. Here we have added the weights to profile curve is 5, and the trajectory curve the weights are 5. So this is one of the swung surface example where this is the trajectory curve and this is a profile curve, where both combined gives to result this form of a tubular shape. And to be honest, any kind of surface or any kind of object can be formed through swung surfaces, because they can give the kind of expected rotation object which we needed. B-splines skinning is defined as follows: a ck of w of u equal to 102 summation of n I p p I k to the power w, where k is 0 to k be a rational or non-rational section curves. We can assume that all c of u are defined on the same knot vector u and having a common degree p. Then a degree q is determined for the v in the direction and parameters v of k k is 0 to k, and not vector v are computed. These are then utilized to perform n plus 1 curve interpolation across the section curves control points, providing a skin surface controller points q of ij w. As a result, q ij to the power w is interpolating curves jth control point through p of I comma 0 to the power w to p I comma k to the power w. Then the section curves are defined on the following node vectors, where c of 0 is the same cause it is on straight line, it goes 0 to 1 directly, and c of 1 it is going towards up, and then so it goes from 0 to 1 with few middle points like 3 by 10, 1 by 2, 7 by 10. For c2 also it's the same in c3 and c4. So these all are different kind of vectors used for the skinning surface, and we are writing them as a common vector with 0, 0, 0, and combining all of this into a common simple vector. So then if we are considering that then a total of 22 control points in u direction, then this gives the end product, and the design has the uh, surfaced mountain in this shape present right here. Next, although it's simple to formulate, and implementing a strong and usable skinning feature is challenging, and developing skin surface interact is frequently a time-consuming iterative process. Surface shape is difficult to manage. It is determined by the quantity, shape, and placement of the suction curves, as well as interpolation method used in the V direction. Spine curve and 5 planar section curves are this is a spine curve is in cross-sectional curves. One possible positioning of section curves is in this manner. There are many possible forms, but we are considering this form, and the section curves are positioning the parameters v to the k is 0, 0.25, 0.5, 0.78, 1, and section curve parameters u to the k is 1 by 2, 1 by 2, 1 by 2 for all 5. So then next let v to the k, where k is 0 to k be the v values of this point c8 to the v, where the section curves are positioned. Notice in general v kilo is not equal to vk. Now let p underscore k c underscore s v under k d under k c under s, where v to the vk. So then for each I and k, compute a derivative vector dik for each I the fields 2 of k plus 1. Interpolation contains pi of 0, comma p of I to k, and it shall di of I comma 0 to di comma k. So these are some of the derivative computing formulas which can be formed to this. So
I'm Nikhila. I'll be continuing from here. So coming to the skin surfaces, the following figures show the control points of the skin surface defined by the data shown earlier using cubic interpolation with specified derivatives. So the image on the left shows the control point net with specified derivatives, and the image on the right shows the skin surfaces with specified derivatives. Now coming to the next slide. So the image on the top shows the control point net without specified derivatives, and the image on bottom shows the skin surface without specified derivatives. Now moving on to the skin surfaces section curve positioning. The positioning of the section curve has a definite effect on surface shape, just as the positioning of data points in curve and surface interpolation. Now for the images, the spine and section curve parameters are as following, defined by v cap k and u cap k. Now, a spine curve may be used to position and orient the cross-sectional curves in space. The spine curve can also aid in shape control by providing additional constraints. For example, tangent directions for surface interpolation. Although the designs still have spine curve to position and orient the section curves, where there is no obvious way to impose derivative constraints for the v direction interpolation. Now coming to the skin surfaces, the surface shown on the figures may not be as smooth as the section curves indicate. Now the four rational section curves are all C1 continuous in three-dimensional space. They are quadratics, and they are defined with a double knot at u equal to 1 by 2. Now the respective weights of the section curves are shown as C0, C1, C2 and C3. And where C0, C1 and C3 are only C0 continuous in four-dimensional space. After V-directional interpolation, the surface weights are represented by Wi, J. So if we observe, we can see a negative weight at point P3, 2, that is minus 0.75. Now the surface shown in the bottom exhibits only C0 continuous in the U direction. To now, so what is the solution for this problem? So for example, let us take a full circle which can be represented as a degree phi NURBS curve with positive weights and no interior knots. So therefore, it's eliminating the problem. So the general solution for this will be using smoothing function. Now suppose CKW of U is a CR continuous section curve on the knot vector U, whose projection CK of U is CR plus S continuous, where S is greater than 0. Now let f of u be a B-spline scalar valued function on U such that C cap of k w of u equal to f of u into t c k w of u is CR plus S continuous, where f of u is called the smoothing function. Now moving to the skin surface CV state. A skin surface S is a skinning surface for the sequence of sets C0, C1, so on Ck if it satisfies S interpolates the sets and there is a continuous function f S to the 0, 1 and real numbers 0 equal to t0 less than t1 less than so on tk equal to 1 such that Ci equal to f inverse of Ti. Skinning in practice. Now it is a recent term for lofting. The set Ci consists of one or more curves in which they are sometimes called skinning curves. Different skin surfaces are made using different constructions. Change in the order of curves yield different skin surfaces, thus the order is very. Now let us discuss about the surface skinning. It is also called as lofting, where it is a process of passing a surface through the so-called cross-sectional curve. Now coming to the causes of lofting problems, there are four types of lofting problems. They are parameterization inconsistency, positioning inconsistency, continuity inconsistency, weight problems. So in the parameter inconsistency, parameters must flow the same way along each section curve. Now the position inconsistency, the section curves must be placed with care, or wiggles or even self-intersection may occur, so that we may not occur or achieve the required design when designing. So continuity inconsistency are nothing but rational curves must be parametric continuous in homogeneous space, not just in Euclidean space. Moving to the weight problems, large weight changes may cause negative weights during interpolation, and weight scaling may produce nonsensical surfaces. This problem we have seen in the previous example. Now let us discuss about the skinning to approximate cross-sectional curve. So B-spline surface approximation is the method and it has four phases, namely branching problem handling, contour alignment, construction of closed B-spline contour curves on a common knot vector, and surface skinning of the B-spline curve. Branching problem handling is decomposing each multiple branch problem into a set of single branching problems, such that we have to decompose the M and M n branching problems to one single branching problem, such that we have m plus n counters for each implants and elements. Now counter alignment is the next second step. It is to determine a good baseline for each single branching region and align them for the baseline. So it is what is we got in the before step is the single branching problem. So we have to determine a good baseline for all these and then align them to a perfect single baseline. Now the coming to construction of closed B-spline contour curves on a common knot vector, the B-spline curves are required to make compatible for the surface skinning. So here all the B-spline curves that we have got are required to make compatible for the surface skinning. Now the surface skinning of the B-spline curve. By skinning the intermediate closed B-spline curves constructed on the common knot vector, we generate a bicubic closed B-spline surface. Now these are the method of how B-spline surface approximation is done. Now continuing, Let us discuss the several potential hazards which cannot have a satisfactory practical solution. Now, these problems all arise as a result of the fact that surface construction is taking place in homogeneous space and corresponding three-dimensional and four-dimensional geometry can be radically different. For example, let us take two three-dimensional curves which can be smooth, similar in shape and close to one another, while their four-dimensional counterparts may have curves, have totally different shapes and be far from one another. Now, let us discuss more specific problem that can arise are the v-directional surface parameterization may be rather poor. So, for example, let us take two-section curves and multiply all the control points of one of them by a large weight. This does not change the three-dimensional curve geometry, but the skin surface between the two sections is poorly parameterized in the v direction. The three-dimensional surface parameterization can be improved by using the projected control points p, I, k to compute the v bar k. But this can produce wild four-dimensional v directional interpolation, resulting in undesirable geometry both in four-dimensional and as well as three-dimensional space. And the interpolation can produce a negative or zero wi, k even though all the section weights are positive. These cause problems such as system crash downstream in a system. And the surface may not be as smooth as the section curve indicates. Now let us discuss about the um, example shown. So we can see the topmost example. It looks like a pipe. We can design a more complex tube by using six circles which are arranged so that the generator surface would look like a pipe, and also it has a turning 90-degree, and where we can see the leftmost circle is called the profile curve. And let us see the another example where the design contains 9 NURB curves of degree 3 that approximately resemble the shape of the car body. So we can adjust these profile curves to make the design more realistic. The leftmost curve is the first profile curve. Now my friend will be continuing. Thank you.
Hi, this is Vijay. Today we are going to talk about swept surfaces. Swept surfaces are surfaces that are generated from a section curve position along a path. This path is generated by trajectory curve. The main difference between skinned surfaces and swept surfaces is skinned surfaces use many section curves, whereas the swept surfaces use trajectory curve as well as the section curve. Moving on, swept surfaces are generated by moving a section curve along a trajectory curve. Denoting the trajectory curve as T of V and the section curve as C of U, a general swept surface is given by swept surface of curve U and V is equal to trajectory curve V and M of V and section curve C of U, where M of V is a matrix incorporating rotation. The transformation must include translation or rotation and may also include scaling and shearing. Sweep representations are used to construct 3D objects from 2D shape that have some kind of symmetry. Now coming to types of sweep. There are two types of sweeps. One is translation sweep and another one is rotational sweep. Translation sweep is generated by first shaping a polygon with a vertex and then defining its path and then populating the polygon on the same path, so that at the final stage we will get a complete 3D object. Coming to rotational sweep is same as transactional sweep, but the only thing differs is the path of trajectory curve. The path is given so that the sequence of the path is given so that the sequence revolves around the rotation. So Once the once the uh, once you continue building vertex tables as shown in the figure, and at the last stage you will define a surface table as shown in the figure. I also want to illustrate this with one more example, that is a swept tube. With the swept surfaces, a tube does not have to be linear like a cylinder or circular like a torus. One can use a circle as a profile curve and another curve as a trajectory curve. The following shows a circle in the xz plane as a trajectory and a NURBS of degree 3 not in the xy plane as a trajectory. From the wireframe figure shown, you will see that the tube is narrower than the two ends. This is simply because the profile circle moves in parallel with each other. As a result, would stack together near to the place where the trajectory curve does not change shape fast enough. Coming to the swept surface construction, there are three steps in creation of a swept surface. One is refinement of selection, another is extraction of trajectory, and the last one is refinement of trajectory and extraction of profile curves. The shape of the swept surface region is crucial to subsequent and analysis and editing. To ensure this creation, we acquire the smoothness of both the curve and the normal original mesh along the curve. The trajectory extraction is the pivotal step for creating the representation. To create a meaningful swept surface, traditional skeleton is always the ideal choice. The profile curves are extracted to be intersection of the cross-section planes in the mesh. This is the example of an algorithm for creating a swept surface with no trajectory control interpolation. We can take inputs of control points, trajectory, and BV and SV as input functions, and Q and K need to be minimum. Then, by using performing the transfer and positioning, we can generate an output of a swept surface with no trajectory control interpolation. Similarly as the previous slide, but this is different from the above figure. Like, this is a swept surface with a trajectory control interpolation. We take input as a trajectory control point, then BB and SV as input functions, and Q and K needs to be minimum. By performing transformations and positioning, we get a output of a swept surface with trajectory control interpolation. Here the two figures varies by one in swept surface and with no scaling, and another in swept surface with scaling. The first figure used no scaling, so while the other one used a piecewise linear B-spline scaling function defined by the control points. The previous two examples used a planar trajectory curve. These examples show a three-dimensional trajectory. The trajectory was not maintained in the first figure, whereas a trajectory is an iso curve in the surface of the other figure. In both examples, all section instances were scaled with the constant vector. Swept surface problems. Trajectory is interpolated. There are two main swept surface problems. One is self-intersection and wave surfaces. Mostly the most challenging problem in the field has been the identification and the visualization of the boundary, especially for those volumes that are based on free-form geometric entries. Self-intersection. To ambiguous represent a solid volume, it is necessary to identify and trim away extraneous and distracting part caused by self-intersecting region of the boundary surface. Swept surfaces. Incorrect curve placements cause flip surfaces. Sweeping example. Section curve is placed by Freenet frame. This slide shows the better curve placement with a local moving frame. In the first example, trajectory is planar, whereas the second one, it is twisted. In both cases, the moving B of V is drawn with a solid arrow, and the Freenet frame axes are plotted dashed.
Hello, good morning, Professor. Uh, Boinpalli. Today I'm going to present cordon surfaces and cone surfaces. First, let's start with cordon surfaces. Cordon surfaces are spline blending interpolating the network of curves is known as cordon surface. In cordon surface, we are given network of curves as you can see over here. It is decided to construct the surface G of u, v interpolating the given curves. Let us denote the given curves as u curves and v curves. The u curves are represented from 1 to n and v curves are represented from 1 to n. Curves intersect at some points. That point is known as u of ui, vj, where I tends from 1 to m and j is from 1 to n. The basic coordinate function is defined as g of u, v is equals to g1 of u, v plus g2 of u, v minus g12 of u, v. Like here, the meaning is it's adding two surfaces and subtracting the third surface, subtracting the intersecting surface. Here, Li to the power of m of u are blending functions satisfying Li to the power of m of ui is equals to 1, comma, Li to the power of m of uk is equals to 0, where I is not equal to k. Here, we use B2 splines to construct appropriate blending functions. B2 spline surface is traditionally a tensor product of curves defined using piecewise basis polynomials. The basic idea to construct a cordon surface is to take a univariate interpolation scheme applied to all curves, add the resulting surfaces, and subtract the tensor product interpolation that is defined by the univariate scheme. A cordon surface construction. The cordon surface can be constructed using different ways. The first one is unidirectional lofting. In unidirectional lofting, it is constructed by two ways. The first one is by control net, and second one is by surface interpolating the V curves. The next comes the V-directional lofting. V-directional lofting can be constructed by two ways. The first one is by control nets, and second one is by surface interpolating the U curves. The third one is tensor product surfaces. In tensor product surfaces can be constructed by two ways. The first one is by control net, and second one is by surface interpolating the intersection point. Then comes the main cordon surface. The main cordon surface can be constructed by two ways. First one is by control net, and second one is by surface interpolating U and V directional curves. In this one, we add two surfaces and subtract the third surface like basic cordon surface definition says. Next comes the cone surface. Cone surface is a type of manifold parametrization used in computer graphics like CAD to smoothly join other surfaces together and to mesh problem domains into elements in computational mechanics applications, particularly in finite element method and boundary element method. A family of parametric surfaces is called cone patches, was developed by Steve Coons. Steve Coons developed cone patches in 1967. Cone's patch is generated by the interpolation of four edge curves as shown in the boundaries of cone surface. The four patches are defined on the same parameter domain and one boundary curve from each side of a curvilinear rectangle. The resulting surface interpolates these boundary curves and its shape is influenced also by the shapes of constituent parts. Cone surface. The construction presented ensures only a continuous connection of generated surface to the constituent parts. Here we can see the three diagrams. The three diagrams is constructed by using four different parameters. The first one is bumpy surface, the second one is cylindrical surface, the third one is wavy surface, and the fourth one is planar surface. By altering these numbers, we can change the shape of the curves. Like by altering the bumpy surface, by making the bumpy surface to 0 and changing the wavy curve to a maximum value, we can alter these figures. The generalized cone surface is defined by four rectangular surface patches. By changing the shape of the constituents, the shape of the resulting surface will change as well, even if the boundary lines are fixed. This case is illustrated by changing the bump on the patch in front. Next comes the bilinear cones path. Bilinear cones path is a class of cones patches which is obtained when there are four boundary curves and the blending functions are linear. Suppose that we want to create a surface P of u comma v over the unit surface that interpolates the four boundary curves P u naught of u, comma P ui of u, comma P ov of v and P iv of v, which correspond to the bottom, top, left, and right of the square as shown in the figure. That is, we want P of u naught of u is equals to P of u of o, comma P of ui of u is equals to P of u comma I, and P of ou of v is equals to P of ov, and P of iv of v is equals to P of iv for all u and v surfaces. For surface modeling applications, P will typically be a 3-vector. That is, P of u comma v is equals to Px of u comma v, comma Py of u comma v, comma Pz of u comma v. The Coon's patch can be generalized to arbitrary dimensions. Next, the bicubic Coon surface. Parametric bicubic surfaces has different kinds of surfaces. Like the first one is Hermite surface, second one is Bezier surface, the next one is B-spline surface. In parametric bicubic surfaces, we have Q of t is equals to t into m into g from parametric curves. Here, then we replace t with s and need a parameter in other direction, that is q of s is equals to s into m into g. The parametric bicubic surface is known as q of st, which is equal to s into m into g into m into t, where s comma t are greater than 0 and less than or equal to 1. This is the basic matrix of bicubic surfaces. G is equals to g of 1, 1, g of 2, 1, g of 3, 1, g of 4, 1, similarly downwards. Next, construction of Coon surface. The rule surface has 4 interpolants, that is q of ot, q of 1 comma t, q of s comma 0, q of s comma 1 are straight lines, as you can see in the below figure. We know that this is the basic matrix of bicubic surfaces, as we can see over here. And when we expand this surface, we can see this matrix comes. The upper left 2 by 2 matrix consists of x coordinate of 4 corners, and the upper right and lower left matrix gives coordinate of the tangent vector along each parametric direction. The lower right 2 by 2 matrix is the partial derivatives with respect to both s and t, and it is called as twist. Next, Hermite surfaces. Hermite permits C1 and G1 continuity from one curve segment to the next. Conditions for C1 continuity are that the control points along the edge, the tangent vectors, and the twist vectors to be equal. For G1, the vectors must have the same direction. Comes the Bezier surfaces. These Bezier surfaces are derived the same way as the Hermite surfaces. X of s comma t is equals to s into mb into gb into mb to the power t into tt. These are the basic definitions of Hermite surfaces. The geometry matrix G consists of 16 control points, as you can see in the figure. Bezier surfaces are attractive in interactive direction. The surface interpolates some control points, which is known as convex hull subdivision. The C0 and G0 are created by making 4 common control points equal. G1 occurs when 2 sets of 4 control points on either side of the edge are collinear with the points on the edge. Bezier surface can be represented by the equation x of s comma t is equals to 1 minus t cube plus 3t into 1 minus t square plus 3t square into 1 minus t plus t cube into g of px into the matrix which is shown over here. Next, B-spline surfaces. B-spline surfaces are represented by the equations we see below. B-spline surfaces come naturally with C2 continuity. All techniques for subdivision and display carry over the bicubic case. Next comes the design examples of a presentation. The first one is the Schwank surfaces. As you can see in the diagram, there is an S-curve over here and there's a semicircle over here. These S-curve and semicircles alter the shape of this diagram. Next comes the skin surfaces. We can see the control points in the diagram. By altering these control points, the change in diagram occurs. Similarly, this way, this is skin surfaces again. By changing the control points in this diagram, we can change the shape of this surface. Next one is Coon surfaces. We can see 4 patches in the cone surfaces on 4 corners over here. These define the shape of the cone surfaces. Next one is coordinate surfaces, which is similarly constructed with like cone surfaces. Uh, this is the presentation that I want to give. Thank you, everyone.